So we'll see the example based on the interval minus L to L. So today we'll have examples based on the interval minus L to L. So we'll go with the first example. Find Fourier series expansion of f of x equal to 2, and this is x minus 2 less than or equal to 0 less than or equal to minus 2 less than or equal to x less than or equal to 0, 0 less than or equal to x less than or equal to, okay, with period 2 with period 4. So we go with the solution here, right? F of x is equal to 2 and it is x minus 2 less than or equal to x less than or equal to 0, 0 less than or equal to x less than or equal to 2. Okay. T we find in the interval minus 2 to 2 with period 4. So here we have the example, the function defined in the interval minus 2 to 2. And hence, this is the interval minus L to L. So we have period 4, and hence we can write we have L is equal to 4, and hence L is equal to 2. So once we identify L is equal to 2, then we need to find, or we need to write the Fourier series expansion for the function in this interval. Now here we can identify this function is neither even nor odd, and so we write the Fourier series expansion of f of x is given as, what you can have is, we have f of x is equal to a0 plus summation n running from 1 to infinity an cos of n pi x by 2. Please replace this L by 2, and then plus summation n running from 1 to infinity n sine of n pi x by 2. Okay, let this equation 1. Now we have to write the formula for a0, an, and bn. So we can write where a0 is equal to 1 by 4. Then we have this is minus 2 to 2 f of x dx. Then we have an is equal to 1 by 2 integral minus 2 to 2 f of x cos of n pi x by 2 dx. And we have an is equal to 1 by 2 integral minus 2 to 2 f of x and sine of n pi x by 2 dx. Okay, so these are the formulas that we have. Now we have to find this one by one. You can see there is a discontinuity at 0. Okay, so how this function will look like if we draw the graph of this function. Okay, so this is going to be minus 2, this is going to be 2, and here we have is going to be, so this is 0. So how this function will look like? From minus 2 to 0, it is going to be 2, and from 0 to 2, it is going to be x. So this is f of x. Now this function has a discontinuity at 0, and hence we have to split this integral minus 2 to 2 into two parts. Okay, so let us evaluate these coefficients one by one. So first we consider a0, then this is 1 by 4, then this will be minus 2 to 0 f of x dx plus 0 to 2 f of x dx. Now put the value of this function in the interval minus 2 to 0 and 2 to 0 to 2. So we have 1 by 4 minus 2 to 0. The value of f of x is 2 plus 0 to 2. The value of f of x is x dx. So we have the integral. So this will become 2x, the interval minus 2. This is going to be 2x. So interval is minus 2 to 0. And plus this will be x square by 2. Interval is 0 to 2. Now let us apply these limits. So if we apply this limits, we get a0 is equal to 1 by 4. So here, if I apply this limit, this will be 0 minus 2 into minus 2. Okay, this is for the first integral, plus for the second integral, we have 4 by 2 minus 0. Okay, now simplify this. So we have, this is 1 by 4. This minus 2 will become plus. So we'll be having plus 4. And this is going to be plus 4 by 2. That is going to be 2. So we have, this is 6 by 4, which I can write as 3 by 2. So we get the value of a0 equal to 3 by 2. So let this equation 2. Now we have to find out the value of an. So let us find the value of an. So we have an is equal to 1 by 2. Now again we have to split this integral into two parts. So we have minus 2 to 0. This 2 into cos of n pi x by 2 dx, plus we have 0 to 2 x into cos of n pi x by 2 dx. Okay. So we can see this integral is easy to integrate, but for this integral we have two functions. So this we consider as u and this we consider as v, and hence we have to use u into v rule here. So we can write, hence using generalized biparts rule, we get. So what we are able to get here, see, we have an is equal, is going to be 1 half. For the first integral, we have this is 2 into sine of n pi x by 2 upon n pi by 2, and the limit are minus 2 to 0. Plus, for the second integral, this x remains as it is, and now the integral of cosine. So we have sine of n pi x by 2 upon n pi by 2, and then minus the derivative of this is going to be 1, and hence the integral of this minus cos of n pi x by 2 upon n pi by 2 bracket square, and the limit is 0 to 2. Okay, so that's what we have. Now we need to simplify this. So what we know is, we know since if I put 0, I'll be getting sine of 0. If I put minus 2, then I'll getting a sine of minus n pi. So sine of minus theta is sine of minus sine of theta. So sine of n pi. And hence I'll be having sine of n pi is equal to sine of 0 is equal to 0. So what we say, that is the sine terms in above equation vanish at minus 2, 0 and hence we have, what will be having, an is equal to, this is half of, this term is going to be 0 at both the times, this term is going to be 0 at both the times, and hence this minus minus will become plus. So I'll be having cos of n pi x by 2 upon n pi by 2 bracket square, and here the limits are 0 to. So we can simplify this as, this is going to be half of, we have this 2 upon n pi bracket square into cos of n pi x by 2. And this is being a constant, we have to apply the limits for this term. Now let us simplify. What will get here? So this is 1 by 2. Then you'll be having 4 upon n square pi square. And what will be the limit? So I'll be having cos of n pi minus cos of 0. Okay. So we get here, if I put 2, then this 2 will get cancelled, and then I'll be having cos of n pi minus cos of 0. So what we know is, we know the value of cos of n pi is equal to minus 1 raised to n, cos of 0 is equal to 1. Here this 2 will get cancelled, so 2 upon n square pi square, and here I'll be having minus 1 raised to n minus 1. So this is an. Now when we have this terms, okay, so what we know is, we know if we have minus 1 raised to n plus or minus 1, or 1 plus or minus minus 1 raised to n, then check for n is even and n is odd. So what happens, we have to check when we have any one of this term. Okay, so now what we have here, so we have one of the term minus 1 raised to n minus 1. So we have to check if n is, if n is an even, then we have minus 1 raised to n is equal to 1. So this term goes 1. So 1 minus 1 is 0, and hence an will be 0. Now if n is an odd, then what you get is minus 1 raised to n is equal to minus 1. So this will be minus 1, this will be minus 1, minus minus 1, minus 1, minus 1, minus 2, and this we have. So an becomes minus 4 upon n square pi square. So that's what you will be having equation 3. Now we got the value of a0, we got the value of an. Let us find the value of bn. Okay. Now we have bn is equal to, half of minus 2 to 0 2 into sine of n pi x by 2 dx plus we have integral 0 to 2 x into sine of n pi x by 2 dx. Okay. Now again, this integral is easy to integrate. So here we have u into v. So we have to use u into v rule for this. And now we use using generalize by parts. So we get Vn is equal to 1 half. For this integral, we have the integration 2 into minus cos of n pi x by 2 upon n pi by 2. So it is minus 2 to 0 plus. Now for this integral, we have to use generalized by part rule. So u remains as it is, that is x. And then the integration of this term. So we have minus cos of n pi x by 2 upon n pi by 2 bracket square. So here we get n pi by 2. Now minus the derivative of this x is going to be 1 and the integration of this term. So we have minus sine of n pi x by 2 upon n pi by 2 bracket square. The limit for this are 0 to 2. Now, what we know is the sine term will vanish at both the ends, 0 and 2. So we have, since sine of n pi is equal to sine of 0 is equal to 0. That is, what we can say is the sine terms vanish in above equation at 0 and 2. And hence, we have, so what we'll be having, we'll go get Bn is equal to half of, here I'll have, this is 2 upon n pi, minus I'll take here 2 cos of n pi x by 2, and the limit is minus 2 to 0. Plus, we'll have here, is going to be minus 2 upon n pi x into cos of n pi x by 2 and 0 to. Now, let us apply this limit. So here I have minus, here I have minus, I can take it out. Then here I have minus 2 upon n pi. So here also we have 2 upon n pi, we can take it out. And hence we have minus 1 half into 2 upon n pi. And now what we have inside, here we have 2 cos of n pi x by 2. The limit is minus 2 to 0. And here we have plus, this x cos of n pi x by 2. And the limit is 0 to 2. Please be careful for using the limits. Don't be in hurry. Write down the proper limits. So this 2 and this 2 will get cancelled. We'll have 1 upon n pi. Now apply the limits. So if I apply 0, I'll be having twice cos of 0 minus twice cos of n pi. Okay, because I'll put this minus 2, I'll be having minus of n pi. So cos of minus n pi is same as cos of n pi, as cos of minus theta is same as cos theta. Then plus. So I'll be having 2 cos of n pi. And here we have minus 0. So this term will get cancelled with this term. We'll have only this term. And hence we'll have minus 2 upon n pi. So this is Bn. So we got the value of Bn at this equation 4. Okay. So here we got the value of An, we got the value of A0, and we got the value of Bn. So we are able to write the Fourier series. So what we can say is, from equation 1, 2, 3, and 4, we have f of x is equal to, please be careful here. So we'll be having 3 by 2 minus 4 upon pi square summation n running from, here we have to be careful. Okay. So what is an we have? Okay. So see the an. So this an exists only if n is odd. Okay. So this an exists only if n is odd. And that's why we have to write here. Okay. So while writing the Fourier series, we have to write here, this only exists if n is odd, and we have cos of n pi x by 2 plus summation n running from 1 to infinity. En exists for all the terms. Okay. So we can have, this is minus 2 upon pi summation n running from 1 to infinity 1 upon n, and you will be having sine of n pi x by 2. So this way we are able to get the Fourier series for the function in the interval minus 2 to 2. Okay. So do you have any doubt in this example? Do you have any doubt here? Okay, now that's great. You don't have any doubt. So we'll go for the another example in the interval minus L to L. So let us see another example. Find Fourier series expansion of f of x is equal to x square in minus L to L. So we got the solution. Wait, f of x is equal to x square be defined in minus L to L. So here the length is 2L and L is same as L. So we don't have any problem. It is already in the standard interval minus L to L. So here we don't have to find the L. Okay. And now identify whether this function is a even function or odd function. What do you think, whether this function is a even function or odd function? So you are supposed to identify it directly. So whether this is going to be an even function or it is going to be an odd function. Yes, you got it. So it is going to be an even function. Correct. So whatever I have shown you how to identify the even function or odd function, you need not write it in the examination. You can directly identify the function and go for it. Okay. So here now you are able to identify the function. So you identified the function, and hence we are ready to go for it. So directly you can write that this is going to be an even function. So we say here hence f of x is an even function. So if it is a even function, what we know is then we have straightforward we can write bn is equal to 0. Okay. So here we get bn is equal to 0. And once you have bn is equal to 0, you can write the Fourier series. So we have the Fourier series expansion of f of x is given as, okay. So what do you have? F of x is equal to a0 plus summation n running from 1 to infinity an cos of n pi x by l. Let this equation 1, where please be careful now. So a0 is equal to 1 upon L integral 0 to L f of x dx, and an is equal to 2 upon L integral 0 to L f of x cos of n pi x by L dx. So this example, we have to find only a0 and an. Now let us see. So what we get here, we consider this one by one. So consider a0 is equal to 1 by L integral 0 to L. We have x square dx. Okay, so that's what you will be having here, because our function is x square. And now integrate this. So 1 by L integral x cube by 3 and 0 to L. So 1 by L will be having L cube by 3, and then the lower limit is 0. So we have 1 by L cube by 3. So L you can cancel, and hence we can get a0 is equal to L square by 3. So this is the value of a0 or equation 2. Now once we get the value of a0, we have to find what is the value of an. So now we have an is equal to 2 by L integral 0 to L x square cos of n pi x by L dx. So here you can see we have two functions. This is going to be u and this is going to be b, and hence we have to use u into b rule. Okay, so we'll use u into b rule, and hence we can say using generalized by parts rule. So using generalized by parts rule, we have, okay. So what we have now, see here. So an is equal to 2 by L, and here this x square remains as it is. So the integration is going to be sine of n pi x by L upon n pi by L, then minus the derivative is 2x, and here we have minus cos of n pi x by L upon n pi by L square. Next term is plus, the derivative of this term is going to be 2 and integration of this. So minus sine of n pi x by L upon n pi by L. Okay, and the limits are 0 to L. So what we know is, we know this sign terms vanish. So we have to mention it, since sine of n pi is equal to sine of 0. Because if you use L here, this L will get cancelled and you will get sine of n pi. If you use 0, you will get sine 0. So these both the terms are going to be 0. So that is what we say is the sine terms in above equation vanish at 0 and L, and hence we get so what we'll get here, we have an is equal to, this is going to be 2 by L. So this term is vanishing, this term is vanishing, minus minus will become plus. So we have 2x cos of n pi x by L upon n pi by L square, and we have 0 to L here. Okay, so I can write this as, this 2 I can take out, and then this term also I can take out. So I can write 2 by L, this is 2, and this will become L by n pi square. What remains inside is x cos of n pi x by L, and here we have the limit 0 to L. Now simplify this, so we get, this is 4L square upon L n square pi square, and here if I apply L, so I'll be having L cos of n pi minus I'll be having 0. So what we have is, this is 4L square upon L n square pi square, and here we have L into minus 1 raised to n. So this L and this L we can cancel, and then we can write 4L square into minus 1 raised to n upon n square pi square. So we got the value of an, and that is equal to 4L square minus 1 raised to n upon n square pi square. So we got the value of an, we got the value of a0, and hence we are able to write the Fourier series for this function. So hence from equation 1, 2 is going to be 3 and 3, we get, so what we are able to get is f of x is equal to L square by 3 plus 4L square on pi square summation n running from 1 to infinity minus 1 raised to n upon n square cos of n pi x by L. Or what was the function? X square. So x square is equal to L square by 3 plus 4L square by pi square summation n running from 1 to infinity minus 1 raised to n upon n square cos of n pi x by L. So that's what we have, the Fourier series for the function of x. Okay, so this way we are able to get the Fourier series for the function. So do you have any doubt in this example?
No, sir.
That's great. So you don't have any doubt. You are getting everything good. Okay. So let us try one more example based on this. Okay. So we go for the another example. Okay. Now we have obtained the Fourier series expansion for f of x is equal to sine of x in minus L to L, where a is not an integer. Okay, so this is precisely given that a is not going to be an integer. Okay, now let us we have to find. So let f of x is equal to sine of ax be defined in minus L to L, where a is not an integer. Okay, this is given. So now, can you tell me whether this function is a even function or this is an odd function? Can you identify this function, whether it is even or odd? Remember the definition of even and odd function? Okay. So while defining the even function and odd function, we have taken an example of cosine function. Cosine function is an even function. And we have taken the example of sine function. So sine function is an odd function. Okay, so that's why we have here sine of ax, that is going to be an odd function. Okay, so once you identify that it is going to be an odd function, then you are able to write it directly. So we know that this is going to be an odd function. So what we can say is, since f of x is an odd function, hence we have. So what we have here, a0 is equal to an equal to 0. So directly we'll be having a0 equal to an equal to 0. And hence we can write the Fourier series expansion for f of x is given as, what you have, f of x is equal to summation n running from 1 to infinity. Now see, a0 is 0, an is 0, so there remains only bn. And you'll be having sine of n pi x by L. So let it 1, where Bn is equal to 2 upon L integral 0 to L f of x sine of n pi x by L dx. Now we just have to evaluate this. So we have Bn is equal to 2 upon L 0 to L. So it is sine of x sine of n pi x by L dx. Okay, so now we have to evaluate this integral. So what we know is, we know the sine of A. Okay, so what we know is sine of A into sine of B is equal to half of cos of A minus B minus cos of A plus B. Okay, so using this formula, we are able to write 2 by L, 0 to L, half of, we have here cos of ax minus n pi x by L minus cos of ax plus n pi x by L, and here we have this is dx. So this 2 will get cancelled. We'll have 1 upon L, 0 to L. If I simplify this is going to be cos of AL minus n pi x by L minus cos of AL plus n pi x by L, and this is dx. So remember that I am taking this L by x by L common, and so I'm getting this one. Now let us integrate this. So we have, this is 1 by L. The integration is going to be sine of AL minus n pi 2x by L upon, here we have AL minus n pi by L minus sine of AL plus n pi x by L, and here we have the term, see the term here, so it will become AL plus n pi, and we get here by L 0 to L. So here we have to be careful that this sign will not vanish because a is not an integer. So that's why we need to remember the condition that this, yeah, a is not an integer. So we have to be careful. And now apply the limits. So 1 by L, this I'll have L upon AL minus n pi, and you'll be having sine of. If I apply L, so this will get cancelled. It will become AL minus n pi minus, this will become L upon AL plus n pi, and you'll be having sine of AL plus n pi. And if you apply 0, this term will be 0, sine 0, 0, and this term will be also 0. So minus 0 plus 0. Now you can see what is the common term that we can have. So I'll be having only L common, and this L will get cancelled with this L. So we'll have 1 upon AL minus n pi sine of AL minus n pi minus 1 upon AL plus n pi and sine of AL plus n pi. Now we have to simplify this. Okay. So what we know is we have to simplify these terms. So we'll simplify sine of A plus or minus B is equal to sine A into cos B plus or minus cos A sine B. And hence what we have here, sine of AL plus or minus n pi. So it is sine of AL cos of n pi plus or minus cos of AL sine of n pi. So we know sine of n pi is going to be 0 and cos of n pi is minus 1. So this is minus 1 raised to n, and sine of AL plus or minus this is going to be 0. So for this term we get this value, and for this term also we get this value. And hence we are able to write this as, this is equal to 1 upon AL minus n pi minus 1 raised to n and sine of AL. This term we have minus 1 upon AL plus n pi minus 1 raised to n sine of AL. So this is going to be common again, and hence we have minus 1 raised to n sine of AL 1 upon AL minus n pi minus 1 upon AL plus n pi. So minus 1 raised to n sine of AL, and now here we have AL plus n pi minus AL plus n pi and upon this will become a square L square minus n square pi square. Now we can cancel out this, and then we'll get, so Bn is equal to minus 1 raised to n sine of AL. Here you will get 2n pi upon a square L square minus n square pi square. So this is the value of Bn we have, and hence we can say from equations 1 and 2 we get, so what we'll get here, f of x is equal to 2 pi sine of AL. These are the constant terms. Summation n running from 1 to infinity n into minus 1 raised to n upon a square L square minus n square pi square sine of n pi x by L. So this is what we'll have the Fourier series for this function. So do you have any doubt in this example? Do you have any doubt? No doubt. Okay, that's great. So no problem. That's good that you don't have any doubt in this